So we're going to continue looking at our parametric equations and combine them with vectors today by looking at what are known as the vector equations of lines. All right, and here you see what we did on our last class with parametric equations. We were able to express three-dimensional situations with three parametric equations. All right, so we're able to look at our x position, our y position, and our z position all as functions of time. Okay, so as we're looking at this, keep in mind this is we're combining this idea with the concept of vectors. All right, so let's first of all talk about what the vector equation of a line is. Okay, we looked at planes, curves in the plane, our last unit, and there we just kept it to 2 dimensions with x and y, and we were looking at the projectile motion and all of that. You will not have to write those functions, okay? However, you are going to need to be able to write equations of lines using vectors. And the nice thing is, it's actually pretty easy, okay? The equation of a line in vector form is an equation that gives us a position of an object moving at a constant velocity. That constant velocity is important because if it weren't constant, then we wouldn't have a line, okay? The ones that we were looking at on our last class did not have a constant velocity. Okay, their horizontal velocity was constant, but their vertical velocity was changing because of gravity. Okay, here we're going to be looking at things that are on a particular trajectory, and it's just constant velocity there. Okay. So let's look at, in general, what this equation looks like. Okay, we have the vector r, this is commonly used as our position vector, equals a plus t times b. Okay, now look here, it says that a is the position vector at a time 0, and b is the velocity vector. And then t is our time elapsed. So r equals a plus tb. You might remember last lesson here, remember that they were using x sub 1, y sub 1, z sub 1 in the little formula that they gave, and I said we're going to use x sub 0, y sub 0, z sub 0. This is why, because I don't want there to be any confusion. A is the position vector when the time is 0. So if you think about it here, guys, our position vector, remember we said if A is a point, x sub 0, y sub 0, z sub 0, that's point A. The position vector is its position relative to the origin. So this little a here would be vector OA, okay? Now the nice thing is that its components are simply x sub naught, y sub naught, z sub naught. And if you remember when I mentioned position vectors at the beginning of our study, we said that that was going to be useful if we had a point and then we needed to use it with some vectors. We could represent the point as a position vector and then be able to combine it with other vectors. Well, that's exactly what we're doing here. This A is taken from that starting point, and we're combining it with a velocity vector using time. Okay, so we have to use that position vector. B is our velocity. It's simply going to be 3 numbers, okay, and the reason why it's 3 numbers and not 3 expressions is because our velocity is constant. Okay? So, putting these two ideas together here, if our starting position or our position vector at time 0 is x sub naught, y sub naught, z sub naught. And you can see here what we're multiplying the time by in each case. What do you think our velocity vector is going to be?
0.
No. What?
ABC.
ABC, okay? Our velocity vector is simply A, B, and C. The values that we're multiplying t by in our parametric equations. So this gives us the component vector form of this line, and that is our position x, y, z, or you could say vector r, equals x sub naught, y sub naught, z sub naught, plus t times ABC. Okay? So, these are the same thing. This is our vector A. Okay? This is our vector A. And this right here is our vector B, our velocity vector, ABC. Okay? Is everyone with me here so far? Okay? So, let's examine this a little bit with an equation. We'll start with one in 2 dimensions, okay? Got it? Okay? Alright, so let's start with one that's just in 2 dimensions, and then and we'll see some of the different things that we can do with this, okay? Here is a vector equation of a line. What would this object's starting position be?
-2, 5.
Very good, -2, 5, okay? -2, 5. When you're thinking starting position, it's kind of like when you had y equals mx plus b. Your y-intercept was that thing that was added on, okay, that did not have the variable with it. Well, in this case, it's the part that's added on that doesn't have that parameter t with it, okay? So that's your starting position, -2, 5. What's our velocity in this case?
2, 1.
Good, it's the vector 2, -1, okay? So b, the velocity is that. We could write this as a point, that's our position, okay? Or if we write it as a position vector, A is -2, 5. Okay. Now, what would the x parametric equation for this line be?
Would it be -2 plus 2t?
Okay, very good. -2 plus 2t. -2 is our starting horizontal position. We have a velocity of 2 units in the horizontal direction. So it's -2 plus 2 times t. Okay? What about the y parametric equation? What, Marco?
5 minus t.
Good. 5 minus t. 5 here, a -1 times t. Okay? Now, one easy way to do this if you have trouble seeing it would be to actually do the vector operations. Okay? Think of it this way. If I had -2, 5, I could take this t and distribute it in, right? I could make it 2t and -t. And now I just have 2 vectors added together. Alright? Well, now I can add those together, -2 plus 2t, and 5 minus t. Okay? There you can see your 2 parametric equations. The x is -2 plus 2t, the y is 5 minus t.
So those are all vectors, not points, right?
They're all vectors. Yeah, this is the vector equation. So this is where the notation can get a little bit tricky, but yeah, when you see it in the vector equation here, those are all vectors. Okay, so now that we know this, let's find a couple of points. Okay? Make sure we can still see our parametric equations. Where are we when t equals 0?
Negative 2, 5.
Very good. Negative 2, 5. Alright, so there's our point. I'm gonna write a t equals 0 here. Okay? How about when t equals 1?
0, 4.
Okay, negative 2 plus 2 is 0. 5 minus 1 is 4. So 0, 4. Okay, good. That's t equals 1. And by the way, I know this is a line, right? So I actually could sketch it now. I only need 2 points to give me a line. But let's find these other points as well. When t equals 5, where am I?
8, 0.
Good. Negative 2 plus 10 would be 8. 5 minus 5 is 0. So this point right here is 8, 0. 1, 2, 3, 4, 5, 6, 7, 8. And that happens when t equals 5. Okay? And then what about at t equals negative 2?
Negative 4, 7.
Negative 6, 7. Okay? So 1, 2, 3, 4 more.
Not yet.
Here's 5, 6, 7. That's alright. Alright, so there we are at t equals a negative 2. Okay? So, there we're just finding points. But I want to consider here the question over here, because this is very much like that did we hit a home run problem. Okay? When we were asking, did we hit a home run, we had to look at that one of two ways. We had to say, okay, how high is the ball when it's 314 feet away from home plate? Because that's how far the fence was. And the fence was 10 feet high. So we needed y to be bigger than 10, right? So what did we have to do? We had to take the x and solve for what t would be at 314. Then we could figure out what y equaled. Okay? We could also have done that problem the other way. We could have said, okay, when will y equal 10? When will we be 10 feet off the ground? Okay, and obviously that would happen once on the way up, but then on the way down, if it didn't get down to 10 feet until after we passed 314, we knew it was a home run. Okay? That concept is what we can use right here, or is what we would use if we wanted to figure out what t and y were, but we knew a particular value for x. Okay? Here we know what t is, so we're just plugging it into the parametric equations. But in this case over here, we want a specific value for x. Alright, so here's 8, 9, 10. Where and when is this? Okay? We know it's the point 10 something. But we don't know what that is, and we don't know what time that occurs. Okay? So, how would we figure this out?
You just plug in 10 for x.
Alright, plug in 10 for x. 10 equals negative 2 plus 2t. So t ends up equaling 6. Okay, so now I know that that's where t equals 6. So now what does the y equal? Negative 1. Okay, y equals 5 minus 6, negative 1. Alright, see how that works? anytime you're trying to solve a problem, if you have a particular goal for one of the variables to equal something, then you can plug that value into the appropriate parametric equation and figure out what the other things equal. Okay? Yes?
Would you ever be able to like, or would you ever want to just solve for t on the x side and then put that into like the y thing? So like if you want to graph it on your calculator.
Actually, what you're describing is what we would have to do if we were trying to convert this into what's called a Cartesian equation, which I didn't give you one on tonight's homework, but I did give you one on tomorrow's problems. You're giving an equation of a line, and then you're giving it as a Cartesian equation, okay? If I wanted to get something and kind of eliminate the parameter just to look at its position, I could say, okay, well, I'm going to write, let's say y, using my y equation, t would equal 5 minus y. So if I plug that in for x, x would equal a negative 2 plus 2 times 5 minus y. And notice I've eliminated the parameter now. I have an equation that's just the Cartesian coordinate system. Time isn't involved here. So you can do that. We're not going to make a huge emphasis on that, but yeah, you can do that actually with any set of parametric equations. So, all right. Now, let's consider one in 3 dimensions, okay? And I want to consider it in, answering a couple of different questions than the ones we answered with the 2-dimensional one, okay? You can do all the stuff we just did with the 2-dimensional one as well. For example, where is our starting position?
-2, 5, 7, 5, 7.
Okay, good. It's at -2, 5, 7. Okay, and our velocity,
2, -1.
okay, 2, -1, 4. Okay, so here's the question we have. Does an object actually pass through a point 2, 3, 15? Okay. Now here's the part where this can be a little tricky if you're not thinking about it clearly. Okay? Is x going to equal 2 somewhere?
Yeah.
Yeah. Okay? Is y going to equal 3 somewhere? Will z equal 15 somewhere? Okay? So, how would we be able to tell if this line actually passes through that point?
If they all happen at the same time.
That's the key. They have to happen at the same time. Alright? Let's check this out. Okay? Our x, we would need our parametric equation. So our x parametric equation for this one would be what?
-2 plus 2t.
There we go. -2 plus 2t. So we should ask, when does x equal 2? We plug in 2 for x.
Mr. Jackson, why does b equal to -4, 4?
Oh, sorry, that's a 1.
Oh,
Thanks.
Sure.
-1, 4. Thanks. So what does t equal here? When does x equal 2? When t equals 2. We add 2, and then we have 4 equals 2t. Divide by 2, so t equals 2. Okay? With me so far?
Yeah.
Liam?
No, I don't understand why it's 2t.
We're getting the parametric equation, -2
Oh.
plus 2t. Okay. For our y parametric equation, we would have 5, and then here's the -1 in the y direction, so 5 minus 1t. Okay? So we're asking, when does y equal 3? Okay? So 3 equals 5 minus t. What does t have to equal? 2. Alright, so we're good so far. If we got a different number here, we wouldn't even bother with z. Okay? Wouldn't even bother using z. But since we got both those times correct, we do have to check the last one. Alright? So let's try z. What would the parametric equation for z be?
7 plus 14.
Good. 7 plus 4t. Alright? So when does z equal 15? We subtract 7 and you get 8. 8 divided by 4, t equals 2. Therefore,
Passes.
yes, it does pass through that point.
That was cool.
Okay? That's going to be something really important to keep in mind as you look at tomorrow's lesson. Tomorrow, we're talking about intersections, and one of the distinctions that we have to make is the lines may cross, but do the objects actually meet each other? Okay? And we'll deal with that in the lesson tomorrow. But it comes down to considering the times that we are at different positions. Okay? All right. You see the parametric equations here. Try this again here for the point -8, 8, and -1. Okay? -8, 8, -1. Do we actually
With the same points.
pass through this point? It's the same vector equations. So here you have your parametric equations. Do you have an answer or a question?
I know the answer now. The coach wanted me to say to prove I will come to this.
Well, when you come to it, just to prove that you are going, or that you made it to it.
Like I said a metric to him, and he said we need to send a metric to him.
Okay, sure. All right, what time do you get here for the x? When is x equal to -8?
-3.
-3. Okay, add 2 and you get -6. Divided by 2, you get -3. Okay, so t equals -3. How about for the y? Okay, y equals 8 at -3. T equals -3. How about our z? -2. Okay, you subtract 7, you get -8. Divided by 4, t would equal -2. So, do we hit this point?
Yeah.
No. Alright? No, we don't hit that point because not all the times are the same. Okay?
If they were, we hit the point.
If they were, we would have hit the point. But in this case, we were at the right x and y position, but we were, in this case, maybe too low or too high. Okay, here's the thing, and we're shooting at it, alright, and we missed, okay? So, all right, any questions about that? It's not terribly difficult, right? You just gotta kind of try to isolate things. One of the things here, guys, especially those of you who tend to be sloppy, okay? You've got to try to stay organized. If you keep things nice and organized, write down your parametric equations, keep things organized. You're not just like writing all over wherever you feel like on the paper at that moment, okay? If you keep things organized, it makes these problems a lot easier as well, okay? Now, that's it as far as the new stuff we want to look at today, okay? So what I want to give you at this point is an opportunity to start working on a couple of these problems, okay? So here, there are 4 different lines that are being described. So write it as vector equation and then as parametric equations, all right? So to get the vector equation, you need your starting position and a velocity, right? Just like in when you were getting equations of lines before, you needed the slope and a point. Now you need a starting position and a velocity, okay? So, by the way, when it says a line parallel to, they're giving you a direction vector or a velocity vector, okay? So, in this case of part A, I know the language is kind of strange there, but they're giving you that velocity. Sometimes they'll say it's parallel to something else, and you got to figure out, okay, what would my velocity have to be parallel to that? Okay? So I'm going to give you guys time to work on this in the last 15 minutes here. Yeah, absolutely.